Hello viewers, welcome to add-on. In this question, we are asked to draw a niche gauge and describe the structure and working of N-channel JFET and also draw the drain characteristic curves. Okay, so JFET is junction field effect transistor. Okay, JFET is a junction field effect transistor which is one of the criteria, or we can say one of the field effect transistors. Okay, so this is a voltage control device where the gate voltage controls the operation of JFET. Okay, so there are basically two types of JFET. One is N channel and another is P channel. Okay, so here in our question we are asked to define the N channel JFET. So in the N channel JFET, let us draw the symbol of the JFET first. So for N channel, so the JFET has three terminals. The first terminal is gate, which is represented by this line, and the second terminal is drain, which is this line, and the third terminal is source, which is this line. Okay, so this is the symbol of N channel JFET. So in the N channel JFET, the generation of current is due to the movement of the electrons. Okay, we need to notice one thing, that the N channel JFET, the current is generated due to movement of electrons. But in P channel JFET, the current is generated due to movement of holes. Okay, so in most of our application, N channel JFET is used over P channel JFET because due to the presence of electrons, they provide a better mobility and switching speed. Okay, so this is the main concept of N channel and P channel and the difference between it. Now, these three terminals, gate, source and drain, they are equivalent to the collector, base and emitter in the BJT. But in the BJT had PN junctions. Okay, but the JFET have channels which are made of either P-type material or N-type material. Okay, and the JFET arrow points, which is this point. Okay, so this point is for the N channel JFET, but in the P channel JFET, the arrow will be like this direction. Okay, so this is the symbolic representation field. Now let us draw the N channel JFET. Okay, the N channel JFET is like this. As I have said, the channel will be of N type. Okay, and the N channel JFET, the channel will be of N types, and on the either side of the channel, we will be getting a P type substrate. Okay, so this is our drain terminal. This is our drain terminal. This is P-type material. This is P-type material, and the channel is of N-type. Okay. So this wide region between the two P-type material is the channel region. And for N-channel JFET, as the name suggests, the channel will be of N-type. And on the either side of the N-channel JFET, there will be P-type of substrate. Okay. So at this terminal, we will be getting our gate terminal. And from this terminal, this is our source terminal. Okay, this is our source terminal. Okay, so here we can see the channel is of N type. Okay, in the N channel JFET, we can say that the channel is of N type and the substrate which is made on the either side of the N channel is P type. Okay, so the drain and the source terminal, this drain and the source terminal, these are present on the either side of the N channel. Okay, and a small voltage. Okay, we will be applying a small voltage at the gate terminal to control the current or the flow of the current between the source and the drain. Okay. So this is the construction of the N-channel JFET. Now we will be discussing how how this N-channel JFET works. Okay. So at first, the gate to source voltage, okay, which is the voltage from gate to source, which is represented by V of GS. This V of GS controls the flow of current from the source to drain. Okay. Now, one thing that needs to be explained, that this source terminal, this is the terminal through which the electrons enter the JFET, and the drain terminal, which is this terminal, this is the terminal through which the electrons leave the JFET. Okay. So the main principle behind this is the gate to source voltage. When no gate to source voltage is applied, or we can say the bias is 0, okay, the resistance of the channel will be very low. The channel resistance will be very low. Okay. So if the channel resistance is very low, the current flow will be very high. So when a small drain to source, or the drain to source voltage is represented by V of ds, so if we apply a small voltage between the drain and source, it will cause the current to flow from the source terminal to drain terminal, because the electrons are entering through the source terminal and leaving through the drain terminal. So if we apply a small voltage between drain and source, okay, as the channel resistance is very low, when the voltage bias at the gate to source is 0, so the current will flow to the channel. Okay. Now, when the gate to source voltage is reverse biased, or we can say we are applying a negative voltage at gate to source, what happens? This N channel JFET, okay, this N channel JFET, at first, when no biasing was applied, the depletion region, or we can say the depletion region which is created, because this is a PN junction, right? This is a PN junction and this is a PN junction, okay? This is a P-type substrate, this is a N channel, this is a P-type substrate, this is a N channel. So between these two PN, there is a depletion region, which is like this. And between this two PN, there is a depletion region, which is like this, okay? Now, when VGS is equal to 0, okay, now when the VGS is equal to 0, the depletion region is of moderate size, or we can say the depletion region was not so much effective. Okay. But now when the VGS is negative or reverse biased, as we know, when a junction is reverse biased, the depletion region or the width of the depletion region increases. So now the depletion region becomes like this dotted line. So the depletion region becomes like this. Okay. As we can see, this depletion region almost occupy the entire channel region. So what happens is that when the depletion region increases, the resistance in the channel will also increase. And as the resistance increases, the flow of the current from the source terminal to drain terminal will be gradually decreased. Okay. Now, as we increase the reverse bias, or if we increase the value of the negative voltage at the gate to source terminal, this depletion region will increase a lot much, such that it will cover the entire channel length. Okay. So when it covers the entire channel length, okay, we will be getting a point at which the drain to source current, which is I of ds, which will be almost equal to 0. Okay. The drain to source current, or we can say the current from the source to drain, which will be almost equal to 0. So this point is known as pinch off point, or the mode in which this is operated, it is known as pinch off mode. Okay. So at this point, this is the point, or we can say this is the particular voltage that needs to be applied to the N channel JFET, at which the depletion region will cover the entire N channel, and the current flow through the channel will be equal to 0. Okay. So this is the main working principle of JFET. So now let us discuss the VI characteristics of JFET. Okay. So the VI characteristics of JFET is like this. In the y-axis, we will be getting drain current, which will be in the range of milliampere. And along the x-axis, we will be getting drain to source voltage. Okay. This is the drain to source voltage which we are applying, and this is the drain current. Okay. So at first, when the value of VGS is equal to 0. Okay, as I have said, the channel resistance during that time was very low. So the value of current will be very high at that time. As I have already discussed, the value of current moving to the channel will be very high. So the drain current will be very high. It will be like this. Okay. So it will be like this after reaching this point. Okay. So in this point, as we can see, here is the current was exponentially increasing. Okay. So this is the ohmic region. I will describe each of this region separately. This is this region at this point, the current becomes saturated. Okay. It is neither decreasing or increasing. This is the saturation region. And this region where we can say the curve is straightening up, this is the breakdown region. Okay. And this is the curve for VGS equal to 0. Now, as I have said, when we apply negative voltage to VGS, the resistance of the channel will increase and the width of the depletion region will also increase. So the value of the current will gradually decrease, which is flowing to the channel. So next up, when we apply VGS, which is equal to minus 1 volt, we will be getting a decreased value of current at this point. Okay. Similarly, if we apply VGS is equal to minus 2, VGS equal to minus 2 volt, we will be getting curve like this. Similarly, as we decrease the gate to source voltage, we will be getting a decreased value of current. And after doing this up to a certain step, almost around VGS is equal to minus 5 volt, we won't be getting any current. So that time it will be our cutoff region. Okay. The current will be this straight line along the x-axis. Because as the VDS is increasing, the value of ID will remain the same, which is 0. So this is the cutoff region. Okay. So this ohmic region, this is the region when the gate to source voltage is equal to 0. Okay. And this saturation region signifies that our JFET is on mode and it is active. Okay. And this cutoff region signifies our JFET is in off mode or no drain current is flowing or ID is equal to 0. Okay. Now, what is this breakdown region signifies? So, when the drain voltage, which is V of ds, when this drain voltage exceeds the maximum necessary voltage, suppose this drain voltage exceeds almost around plus 10 voltage. Okay. When this drain voltage exceeds the maximum necessary voltage, current will flow from drain to source without any resistance. Okay. And for this reason, the device will break down and the JFET enters into a breakdown. So, when the value of VDS, this value is typically around 0 to 5 volt. So, when the value becomes greater than this, so during that time, current will flow from drain to source without any kind of resistance. So, the JFET will enter into a breakdown region and after this point, the current will increase straight. Okay. So, for a value of VDS of 10 volt, we will be seeing the current will be rising from 5 to 10 to 15 like this. And what happens during this breakdown region, the current will increase so much, the JFET will burn. Okay, so this is the breakdown region. So whenever we are operating with JFET, we need to make sure that the VDS voltage will be around 0 to 5 volt. Okay, so this is the main structure and working of JFET along with its characteristic curve. Thank you.